In this video, I will talk about limited dependent variable models, and that includes the Tobit model, the truncated regression, and the Heckman selection model. As a brief overview of this presentation, first I will give a few examples of limited dependent variables. Then I will talk about censoring and truncation and their properties, and we'll give a few examples. And then we will talk specifically about the Tobit model, including the coefficients and marginal effects. We will talk also about the truncated regression model, and we will finish up with the Heckman selection model. So, to start, a limited dependent variable means that there is a limit or a boundary on the dependent variable, and some of the observations hit this limit. So what that means is that you have a data set, and the dependent variable has a lot of values that are concentrated either at the lower limit or the higher limit of the data. And the most common example here is zeros. If your data has a lot of zeros and positive values, this is the right type of methodology for that. So in consumer economics, we have the example that the quantity of a product consumed is zero for some consumers and positive amounts for the rest. So again, we have a lot of zeros and positive amounts. In labor economics, if we look at labor supply or the hours worked by women, some women will be choosing not to work and have 0 hours, and others would choose to work positive number of hours. So again, our data would have zeros and positive values. Not a 0, 1 like the Probit and Logit models, but 0 and positive numbers. Next, there could be some capacity issues. For example, the demand for tickets for a game or a conference is censored at the whole capacity or the maximum number of tickets sold. So suppose you have an event and you can sell at most 5,000 tickets. Well, you could have, if you record the data for over many events, then you're going to have a lot of numbers that are less than 5,000, and then you will have some of them would be 5,000, 5,000, 5,000. That would be where the limit is from above. Another way in which this arises is when we have top coding, and this is when annual income data can be top coded at 100,000. So if we have a survey and we record 100,000 for all observations with income above 100,000, so it means if you have any values below that, like 3,000, 5,000, 57,000, and so on, you can record the actual values. But if you're above 100,000, you can check a box saying that's above 100,000. So you see where the problem is, right? Because if you have checked at 100,000, you have no idea what the real value is. It's top coded and it's limited from above by 100,000. So I will talk about censoring and truncation, and several of these points are kind of similar, but I wanted to go over and provide as many examples so you understand the difference. Censoring is when the limit observations are in the sample, only the value of the dependent variable is censored, and truncation is when the observations are not in the sample. So I have two examples here. It will be a censored sample when you include consumers who consume 0 quantities of a product, and truncated sample, you only include consumers who choose the positive quantities of a product. So suppose you're standing in a grocery store and you have a survey of, say, how many boxes of cereal people buy. And so if you ask everyone, and everyone is in the data, including those that don't buy any boxes of cereal, that would be a censored sample. And you will have truncated sample where you say, well, if you don't buy any boxes of cereal, I don't want you in the sample or to get any other information from you. So we will only record information, you will only be in the data set if you have positive values of cereal consumed. So that's one difference. Another one, which is at the second point here, is that the censored sample is representative of the population. Only the mean for the dependent variable is not, because all the observations are included, and the truncated sample is not representative of the population because some of the observations are not included. Again, in the example that I showed you, I talked about before, you could have all of the people that shop at that grocery store be in your data, and that would be a representative sample of everyone who comes. That would be a censored sample, but the mean for dependent variable won't be, because then you have a lot of zeros in the data for people that don't consume any cereal boxes. But for the truncated sample, you won't have the people that don't buy any cereal in your sample, so it won't be representative of the population in general. The next point, the third point that I have there, is that truncation has a greater loss of information than censoring, because you have the whole observations are missing rather than the values for the dependent variables. So here's again two examples. In the censored sample, you have observed people that do not work, but their hours are recorded as 0, and in the truncated sample you do not observe anything about people who do not work. So a truncated sample will have fewer observations, and you will have a higher mean with censoring from below than the censored sample. Why is that the case? Well, because if you throw away the zeros from the censored sample, and now you have the truncated sample that doesn't have any zeros, that mean of the dependent variable would be higher number because it doesn't have the zeros in there. So also the last point that I have here is that because of censoring, the dependent variable y would be incompletely observed value of the latent dependent variable y star. So when we have income y star of 120,000, that will be censored as y equals 100,000 if we have top coding of 100,000. So again, y star would be the dependent variable, which is an income of 120,000, but you won't observe that. In the data, it will be censored as 100,000. So we need to have the right kind of models that would allow for the fact that you have those limit observations in one end or the other. Okay, so here I have the mathematical notation for censoring from below and censoring from above. So if we have censoring from below, the actual value for the dependent variable y is observed if the latent variable y star is above the limit, and the limit is observed for censored observations. So here, if we have the actual hours worked for people who work and 0 for people that don't work. So see this, y would now be the value that we have recorded in the data. Y star would be the actual, the latent variable, which we don't observe completely. So if this y star is greater than the lower bound or lower limit, which in this case would be 0, that would be the actual value. But if y star is less than or equal to this lower bound, which is typically like a 0, then we would have this lower bound. So this is when we have lots of zeros in the data or another number as a limit from below, and then we have the actual values for the numbers that don't hit this limit. With censoring from above, we have just the opposite thing. And this is, say, if people make below 100,000, we would observe their actual income. So if people make below this 100,000 or this upper limit u, we would observe their actual values. But if they have incomes higher than this upper limit, like above $100,000, then we would just observe 100,000 or this u. So again, now you would have data set where you have a lot of these upper limits, like 100,000 or whatever the value is, and then you will have numbers that are below that. Here we have truncation from below, and this is when the dependent variable would be continuous and no zeros would be allowed. That would mean truncated as 0. And so the dependent variable would be observed if they're greater than the lower limit. So in this case, we would observe working hours for a sample of working women, or quantity of product consumed for the sample of people with positive consumption. So again, if this y star is greater than the lower bound, like a 0, then we would observe the actual number. So y would be equal to the latent variable. And in this case, again, we won't have the zeros in the data. It would just be the positive numbers. With truncation from above is that the values of the dependent variable would be observed if they are lower than the upper limit. So we would observe the actual income in a sample of low-income people. So if we say we're not going to have the rich people in our sample, we would only have people that have incomes less than $100,000, and we would observe their actual income, which would be equal to this y star, the latent variable. Okay, so this is the Tobit model, and the Tobit model is also called the censored normal regression model. And here we have y star equals x prime beta plus e. So how is that different than a normal regression model? Well, the only difference here is instead of y, the actual value, we have y star, which is the latent variable, the one that we don't really observe. And some of the values are limited observations. So the most common Tobit model is when the dependent variable is censored from below at 0. And here we have this, if y star is positive, we would record it as y star. And if it's 0, if it's less than or equal to 0, then we would record it as 0. So we will have a bunch of zeros in the data and a bunch of positive values in the data. So if you look at this expression, that's exactly equivalent to this expression, where y, the actual value that we have in the sample, would be equal to maximum of y star, that's the latent variable, and 0. So if it's 0 or below, we would have 0, and if it's above from 0, then we would have the y star, the actual value. So when we estimate Tobit model, we would need to specify the upper limit, the lower limit, or two limit values need to be specified. So for example, you may have a Tobit model where you have, let me come up with a good example. Say the number of weeks worked in a year. So that could be 0 for people that don't work, but it should be limited by 50 weeks a year, right? Shouldn't it? Or 52. I can't remember how many weeks are in a year right now. Okay, but there could be the upper limit also binding. Okay? Or another example could be that you have like percentage data where you have from 0 to 100%. And in this case, you could have in your data both a lot of observations that have zeros and 100% in the data. But you have to make sure that you have the observations, the limit observations are in the data, because if it's possible to have, theoretically possible to hit that limit, but you don't have any observations in the sample, that will be exactly the same as the OLS regression model, and there is no need to use the Tobit model. So again, unless you have like clustering of a lot of zeros or upper limit observations, you don't, only in this case you use the Tobit model. Okay, so here's where things get a little bit more complicated, and perhaps that will become a little more clear after we discuss some of the other models that we have in the sample. So this Tobit model can be broken down into two models. One of them is a probit model, and one of them is a truncated regression model. How? Now remember that the dependent variable is a 0 or positive value. So in this case, you can say that you can model two decisions. One of them is whether or not the dependent variable is 0 or positive, like a 0 or 1 variable. And then if it's positive, then the question is how much. So in the case of how many boxes of cereal you buy, you could have, did you buy cereal, yes or no? So that would be a discrete decision, yes or no. And then if you do buy, then how many boxes did you buy? And now that becomes a continuous variable. So here's the Tobit model for the first step, for the discrete decision of whether or not y is 0 or positive. And here we would have probability of y greater than 0, and this is the CDF of the normal distribution in x prime beta. This is exactly the Tobit model, if you remember from another video. Except that before, here we had like y equals 1. What's the probability of y equals 1? Well, that's the same as the 0 or 1 or 0 or positive. So that is a Tobit model. The second step is a truncated regression model for the continuous decision or for the quantity of y given that y is positive. So what is the expected value of y given that y is positive? That would be x prime beta. But you also would need an adjustment factor because now you have a truncated distribution where those zeros are not there, and you need to correct for that with this term. So this is the equation for a truncated regression model where you estimate the model for only the positive observations and you throw away the zeros. So in the Tobit model, we have noticed that these variables x are the same, and we also have that those coefficients beta are restricted to be the same. So we will discuss another model later on where this wouldn't be the case, where we could have not only different coefficients here, but we could also have different variables there influencing the two decisions. So the last point to make here is that the Tobit model assumes normality like the Tobit model. Okay, so now I will talk about marginal effects. And there are three types of marginal effects that we can calculate in the Tobit model depending on what is our what is the effect that is of interest to us. So the marginal effect for the latent variable are the coefficients themselves. So if you have d of expected value of y star dx, that would be beta, because we had the model y star equals x times beta, and then if you take the derivative, that's actually what you get here. So these would be the beta coefficients. So this is the marginal effect on the desired hours of work, or the latent variable here. The next marginal effects would be for the censored sample in the Tobit model. And the censored sample is the one that has both the zeros and the positive amounts. And so the marginal effect on the actual hours of work for both the workers and non-workers would be this effect that we have here. And you could see this by differentiating the function of the expected value of y. And so practically what you will see is that the marginal effects in the Tobit model would be these coefficients beta multiplied by a positive scale factor. So we will basically be multiplying those coefficients by a scale factor, and that's how we will get the marginal effects for each of the variables. Okay, and the final marginal effects would be for the truncated sample, or only the sample that we have the positive amounts in there. And the marginal effect on the actual hours of work for workers. So this will be the marginal effects of the number of hours worked for those that work positive hours. And this is, well, a very, very complicated expression that is used to calculate those marginal effects. So the last point that I'd like to make is that the marginal effects would show the highest impact of the independent variables for the latent variable, less impact for the censored sample, and even less impact for the truncated sample. And we would see this empirically when we talk about the example later on. But in general, if you have the zeros in the data versus this would be the truncated, the censored sample, and if you don't have the zeros in the data, that would be the truncated sample, which one would have a higher impact? Well, the one that has censored ones as well, because then you have the zeros and you would have a lot more variation in the dependent variable than if you just try to explain the positive amount. And same thing for the latent variable. So we would use different marginal effects depending on what variable is of interest in the study. So for example, if we have a top-coded study of income, the effect on the latent variable will be of interest. And so we don't care about the censoring at 100,000. So we would like to know what is the effect of the independent variable on the latent variable of how much that person's income is actually, rather than the fact that it was recorded at 100,000. So in this case, we would go with the marginal effects for the latent variable, which we're not observing, and not with the marginal effects for the censored sample, which is for 100,000. Okay, so the Tobit model was the one that had the two decisions together in one model. The zero or positive decision, and then the quantity decision, given that you are in the positive side of the distribution. So here we have Craig's model, also called two-part model or hurdle model. And the Craig's model relaxes the restrictive assumption of the Tobit model that the discrete decision and the continuous decision are the same. So here I have an example where older buildings are more likely to catch fire and claim insurance payments, but the payments will be smaller because the buildings are cheaper. So again, here we have the age of the building as an independent variable, and how much insurance payments are being made. Well, older buildings are more likely to catch fire. So we would need a positive effect on that, on the probability of payment, of a positive payment. But if they do make a payment, or we're in the positive part of the distribution, then we would need a negative effect for the building's age on the amount of payment. So this is a case where we would need, if we're to estimate a Tobit model, we would need a positive coefficient on the Probit model and then a negative coefficient on the truncated model. That's not possible since they're combined into one model. But the Craig's model separates those into two models, and that's why it's possible to show this effect. So the Craig's model two-step estimation procedure is the following. In the first step, we have a Probit model for the discrete decision, and this is the probability of y star being greater than 0, and that's the CDF of the normal distribution. And then we have the truncated regression for the continuous decision, where we have the expected value of y, given the y is positive, being this expression. So the only thing that is different here is notice that we actually have this gamma coefficients here being different than the beta coefficients. So we could have different coefficients in the two-step model. Remember that in the Tobit model, if you go back a slide, we would have this to be equal to beta. Well, now that's not the case. Okay. So another thing about the Craig's model, and I'm going to go back up a slide, is that not only that these coefficients here could be different, but we could also have different independent variables. So here, instead of x, we could have a z variable right there. So we could have different variables affecting the decision of yes or no, and then the positive amount once you have made the yes decision. So that's why the Craig's model is a lot more flexible model, and I really would recommend using it instead of the Tobit model. So let's go ahead and now talk about the test for the Tobit one-step model versus the Craig's two-step model. And here we would have the Tobit model if the restriction gamma equals beta divided by sigma holds. So we have the same coefficients in the discrete and the continuous decisions. And we would have the Craig's model if this restriction is rejected. And to test this restriction, what we would do is we would estimate separately the Tobit, Probit, and the truncated regression model. And we would sum up this log likelihoods for the Probit and the truncated regression model, and we will subtract the Tobit model multiplied by 2. So here we have a likelihood ratio test statistic, which would have a chi-square distribution with degrees of freedom equal to the number of independent variables, including the intercept, and we would have the Tobit model would be rejected in favor of the Craig's model if lambda would exceed the appropriate chi-square critical value. So again, if the log likelihoods are kind of similar between the Tobit and the Probit and the truncated put together, then we're okay with the Tobit. If not, then we should go ahead with the two-step model. But the two-step model again has the advantage of using not only different variables, but it could also show different effects or different coefficients. The final model that we will consider here is called the Heckman sample selection model. And sample selection usually occurs when people select themselves into a group. And that typically happens with surveys. You would like to survey people, but turns out that your sample is not representative because certain type of people are more likely to get into the sample than what's representative of the general population. And in this case, what you need to do is you need to correct for that, so that in the second step, when you have your variable of interest, then we would correct for the fact that our sample is not very representative. So here is an example here. We want to study the factors affecting income for working women, and we have the selection decision whether women choose to work or not, and we have only the income for women that work. So in this case, we could have different factors that affect the two decisions. For example, whether women work or not may be influenced by whether or not they have kids, but their income, at least in theory, shouldn't be influenced by the presence of the kids. So in this case, we would have two separate sets of variables for the first step, where is the do you work, yes or no, and then for the second step of what's your actual income. So this sample selection that we talked about is also called incidental truncation, and it is different from truncation that we talked about in a few slides ago. So what we had before is that the truncation is usually at a given value, like a 0 or something like that. But here that's not necessarily the case. So suppose we want to study income, and the truncation would be if the sample is based on high income. So we have a cutoff value, say above 100,000, and then you just study that sample above 100,000. However, what would be incidental truncation, or the Heckman model, is if you use some sort of approximation for the income variable, and you say that your sample could be based on whether or not people have executive jobs. Well, some of the executive jobs may have high income, some of them may not. So we would have a high correlation, but that's not exactly the same as truncating on the income variable. And another point in the Heckman selection model is that typically the dependent variable is not observed if the observation is not in the sample. So we would not know the income for the people that are not in the high income sample. But their income might not be zero. It's just that we don't have that information. And this sample selection would assume that the discrete decision Z and the continuous decision Y would have a bivariate distribution with correlation rho. So here's the Heckman two-step estimation procedure. In the first step, we would estimate a probit model for the selection mechanism. And here we would have probability of Z equals 1 would be equal to the CDF of the normal distribution. And we have here W would be the independent variables and gamma would be the coefficients. So the procedure is that we estimate the inverse Mills ratio coming from this probit model using the PDF and the CDF of the normal distribution. And then we use this correction factor or the inverse Mills ratio right here in the second step, which would be a regression model for the selected sample. So now here we're interested, what is the expected value of Y given that you're in the sample, or Z equals 1, only for those that happen to be in the sample. And that would be X prime beta, but you also have a correction from the fact that you don't deal with representative sample. So this inverse Mills ratio comes from the first step model right here, correcting for the fact that we may not have representative sample. So the interesting thing about the Heckman model is that it may or may not have the same regressors for the selection equation and for the regression, and typically it is advised not to have the same regressors in both steps. And when you estimate the Heckman model, we would see estimates of lambda, rho, and sigma. So they would be reported, and we could interpret those. So this was again a lecture on the Tobit truncated regression and the Heckman selection models. Thank you for watching.